syllabus which we have covered till now. So if you have doubts, and this is just a practice problem. So now we have solved a two-layer problem. So two-layer problem, and this is three-layer problem. So there is a three immiscible fluid, fluid 1, fluid 2, fluid 3. The density are rho 1, rho 2, rho 3, and viscosities are mu1, mu2, mu3. And the flow rate of this fluid is adjusted such that every fluid is occupying 1/3 of the space between these two parallel plates. This is top plate and bottom plate. The space between these two parallel plates is equally shared by all these three fluids. So if this distance is 3b, so up to a thickness of fluid one layer is b, above that there is fluid 2, above that there is fluid 3. Okay, there are three layers. So, and we need to solve this problem. So how to solve this problem? First of all, roll number 49, Jayant.
Yes, sir.
Yeah. Can you tell me how to solve this problem? Jayant? Roll number 5, Aditya.
Yes, sir.
Yeah. Can you just briefly explain how to solve this problem?
So we can start by taking the origin.
Okay. So where you want to take origin? First of all, Cartesian coordinate system.
Yes, sir. Cartesian coordinate system. Yes.
Because these are two parallel plates, and you
Yes,
can
sir.
assume that length is very large. Length and width is large as compared to distance between. So 1D flow only. So Cartesian coordinate system. Where you want to take the origin?
Origin. So in the middle of the bottom and top plate.
Middle.
Yes, sir.
No problem. You can take middle. Anywhere you can take.
Yes, sir. Anyway.
Anywhere you can take.
But it is symmetric around the middle.
Okay. So you want to take the here. So so which will be this axial direction? Say this direction.
Z direction.
Z direction. So which are zero velocity and which are non-zero velocity?
So Vz is non-zero. Vx and Vy will be 0.
Okay, very good. Roll number 11, Chetan.
Am I audible, sir?
Yes, you are audible.
Yes, sir.
Okay. So now tell me. So Vz is non-zero. Yep. And Y is 0. So which momentum balance you will take?
Sir, in Vz direction. So
what will be the component of momentum you will be considering?
Sir, phi xz, phi yz, and phi zz.
Very good. Exactly similar to previous problem. Okay.
Yes,
so,
sir.
How many boundary conditions are needed to solve this problem?
Sir, 6 boundary conditions, sir.
Very good. Because there are three-phase problem. This is three-phase problem. For every phase, you will get a second-order differential equation of velocity. Second-order differential equation of velocity with respect to coordinate. So, two boundary conditions are needed to solve phase 1. Two boundary conditions are needed to solve phase 2, and two boundary conditions are needed to solve phase 3. 6 boundary conditions. So already we have seen in previous problem, the problem is solved by 4 boundary conditions. So certainly solving this problem using 6 boundary condition will be more complicated. Okay, more complicated. So what are these 6 boundary conditions, Chetan?
Sir, one would be fluid 3 and the top plate.
Okay.
One second would be fluid 1 and bottom plate.
What is that boundary condition?
No slip boundary condition.
Velocity of fluid 3 will be 0 here. Velocity
Yes.
of fluid 1 will be 0 here. These are two boundary conditions. Okay, then
Yes.
third one.
Third would be the interface between fluid 1 and fluid 2. The flux would be same. Means
Very good. Flux will be same here.
yes.
Fluid 1 and fluid 2. Then fourth boundary condition.
In the interface of fluid 2 and fluid 3, the flux would be same.
Four boundary condition.
Then afterwards, sir, velocity would be also same.
Okay, so velocity will be same at the interface between fluid 1 and fluid 2. Velocity
Yeah.
will be same between fluid 2 and fluid 3. So 6 boundary conditions are there, and so problem can be solved. So, so nothing is difficult actually. Only the thing is mathematical complexity will be there. Only the thing is mathematical complex flow profile you will get, flux profile you will get. Otherwise, this problem can be solved with a given information. Okay, but certainly it will take a time because there is two more addition of the constants and everything. So it will be time consuming, but you can solve this problem very easily. So, but this was the problem given. Okay, this was the problem given with this given data. Okay, with this given data. Now take out the given data and just let me know if you can add some assumption to simplify the problem. Okay, three immiscible fluids are flowing between two horizontal steady parallel plates of length 0.7 and width 0.7. All the units are in SI units. Okay, say 0.7 meter and 0.7 meter you can take. It is separated by 6 into 10 raised to minus 3 meter. Okay, mm, 6 mm. So all three fluids equal area, shears equal area. So 2 mm will be for fluid 1, 2 mm will be for fluid 2, 2 mm will be for fluid 3. Area in a direction perpendicular to flow. Flow area. Okay, equal flow area. So perpendicular cross-sectional area in a direction of cross-sectional area of flow will be same. The density of three fluids, fluid 1, fluid 2 and fluid 3 are, okay, these are the density of all three fluids. One fluid is 937.58, another fluid is 621.12 and third fluid is 538.36 respectively. The kinematic viscosity of the fluid 1, fluid 2 and fluid 3 are 1.7 into 10 raised to minus 3, 1.61 into 10 raised to minus 3, 1.87 into 10 raised to minus 3. What is the SI unit of kinematic viscosity? Yeah, roll number 12, Anand. Anand,
Hello,
SI unit of kinematic viscosity?
hello, sir.
SI unit of kinematic viscosity.
Hello, sir. Meter square per second. Hello.
Okay, okay. So pressure difference due to parallel fluids. Okay, P0 minus PL is 15 into 10 raised to minus 3 Newton per meter square. All units are in SI system. It is given. Now derive the expression for this flux profile. So derive the expression for flux profile with this given condition. Now take down all the data. Okay, take down all the data systematically and just see whether what simplification, more simplification you can make in this problem. Okay, take down all the data carefully. Okay, and see what simplification you can make this in this problem. Take down and see some input given in a class can be used to simplify this problem or not.
sir.
Uh, any
Sir, yes, sir. The viscosities of all the fluids are coming nearly same. So we can
what is your
consider
roll number?
as
Roll
a
number. Just tell me your roll number.
63.
Okay, 63
63, sir.
Shreyas. Yeah, Shreyash. So viscosities of all the three fluids are same.
Nearly same.
So what simplification you can make in this problem?
So we can say that all the fluids, like we can consider all the fluids are of one phase only. Because if viscosities are different, then we consider them as different
Very good.
phases. No.
That is what based on given data. If you find what is viscosity you got, Shreyas?
1000 kg meter or Pascal second. 1000 Pascal second.
So now
Oh no, sir. Sorry,
this is
one
the
Pascal second, sir.
okay.
1 Pascal.
Anyway, we will see that. So this was the input given in previous problem. So which is the property based on which two material is considered as a different phase in momentum transfer? It is a viscosity. If two material is having same viscosity, so these two material are not different as far as momentum transfer is concerned. I'm not talking about thermodynamics. I'm not talking about reaction engineering. I'm not talking about mass transfer, heat transfer. As far as momentum transport is concerned, if viscosity of two fluids are same, so you need not to consider anything else. Both fluid will behave identically in momentum transfer. So that is what the thing is there. Okay. So this is what you can see. Okay. This is the answers actually. So these are the three fluids. Okay. Three fluids are there. So if we calculate the viscosity, okay, mu by rho is a kinematic viscosity, mu by rho. So mu equals to rho into kinematic viscosity. So this is what mu1 equals to 0.1 Pascal second, mu2 equals to 0.1 Pascal second, and mu3 equals to 0.1 Pascal second. So Shreyas, you got 1 Pascal second?
Yes, sir. Like 10 raised to minus 3 was there. No?
Yes, sir. I also got 1 Pascal second.
Yeah.
1 Pascal second. Kg per meter cube and 10 raised to minus 3. So everybody is getting 1.
Yes,
Okay,
sir.
maybe
It is 1.
okay. So you make it 10 raised to minus 4 then here. If everybody is getting 1. Just let me see if it is 1. Then make it 10 raised to minus 4. So everybody is getting 1 or 0.1. Can you write in chat box how many got 1 and 0.1? Calculator, you need to skip. It is 1 or 0.1. Pratish?
Yes, sir.
It is 1 or 0.1.
1, sir.
Okay. So make it 10 raised to minus 4, then it is 0.1 actually. So that is not main point. Main point is viscosity of the three fluids are constant. You take this, okay, you take this to -4. 1 into 10 raised to minus 4. Okay, it will be something around 1. 10 raised to -4. Make it 10 raised to -4. So viscosity of all three fluids are same. It is close to 0.1 Pascal second. So as mu1 equals to mu2 equals to mu3, and that will be equals to mu equals to 0.1 Pascal second. The viscosity values are same for all three fluids. So this problem can be taken as a single phase problem. Single phase problem, and hence problem can be solved. So instead of this, okay, instead of this, you can consider this top fluid, bottom fluid, and the fluid having a viscosity mu. So there will be three layers. So three layers will be there. So now you can solve this problem. So how many boundary conditions are needed to solve this problem? Roll number 60.
2, sir.
Two boundary conditions. So whether two boundary conditions are there, Aditya?
Yes, sir. Two
What are these
no-slip
two boundary
boundary.
conditions?
Two no-slip boundary conditions are there, sir, for top
Okay.
plate and bottom plate.
So other thing is same. Okay. Now you can take origin anywhere. Okay. You take, some people can take origin here. Some people can take origin. Only the thing is your model equation will change. Your absolute value should not change. That also. So it is not compulsory that you can take origin here, you can take origin here, or you can take origin here. You can take origin anywhere. So accordingly, you should use your boundary condition, and accordingly you will get a model equation. Model equation will change, but this absolute value will not change. That velocity from the bottom plate, okay, velocity from the bottom plate, it will be 0, then 2.95 into 10 raised to -2 meter per second. Okay, this is x in mm from bottom plate, or you can take x in mm from top plate. Okay, and so this will be there. Okay, and this will be the direction, the magnitude will change based on. So here I have taken origin at the center. Origin is at the center, and these are the values calculated. Mass flow rate will be same. Mass flow rate for phase 2, this will be same, exactly same you will be getting. So now can you solve this problem? So this shell balance will be exactly similar to previous problem. Okay, shell balance will be exactly same, and this will be easier, in fact, easier as compared to previous problem. This will be easier now. So only Cartesian coordinate system. So origin can be bottom plate, near corner. Okay, anywhere you can take. That doesn't matter. So velocity is there only in z direction, and it is the function of x only. So shell dimensions, okay, differential thickness will be there in x direction only, because properties are varying in x direction. Length is L, width is W. Okay, so this is shell. So this is exactly similar to previous problem. So you can do the rate of momentum in rate of momentum out, and this gravitational force is 0. Okay, substituting all. So this is what you will get, delta P L divided by x C1. Okay. So, and this is velocity profile, you will get delta P x square minus C1 divided by mu x plus C2. Okay, substituting this C1 and C2 velocity, two velocity boundary conditions are there. Substituting that, you can get the value of C1 and C2. So what are the boundary condition at x equals to 0? So this origin is taken at the bottom plate. Origin is taken at the bottom plate at x equals to 0. Velocity is 0 at x equals to 3. You can take anything. So only the thing is you will get a different C1, C2 value. So it will not change absolute value. It will change only a model equation. If you take a origin, say at x equals to plus 3 by 2b, velocity is 0. X equals to minus 3 by 2, velocity is 0. when origin is at at the center point. When origin is at top, so it will be exactly similar. Okay, x equals to 3 by 2, so this will be here, and x equals to 0, velocity will be equals to 0. So you can take origin anywhere. So you will be getting appropriate velocity profile equation. Here velocity is taken at the bottom. Velocity origin is taken at the bottom. Now solve this problem, get the value of C1 and C2, substitute and get the velocity profile equation. Anybody got this C1 and C2?
C2 is 0, sir.
C2 equals to 0. Yeah. At x equals to 0, Vz is 0, so C2 equals to 0. So again, it will be very easy actually. So getting the value of C1. So this is 3b C1 something. So you can arrange C1 and substitute here. And velocity is 0. You see. So what is C1 value?
Minus 3 delta P by 2L.
Minus 3 delta P by 2L. Okay. Okay, very good. So C2 equals to 0 and C1 equals to minus delta P 3 by 2L into B. B is coming or not?
Yes, sir. Yes, sir. B is there.
Sir, coming.
Okay. Now substitute this C1 and C2 here, get the velocity profile. Substitute this C1 here, get the flux profile. Okay. Substitute this C1 here. So this is C1 and C2. So you will get a flux profile. So this is delta P B divided by L x by B minus 3 by 2. And this is when origin at the bottom. Okay, origin is at the bottom. This is the velocity profile. Now you can calculate. So what was told? Really? You was told to calculate velocity and momentum. Okay. Distance from the bottom plate. So origin was taken at the bottom plate. So you can calculate this. Here also hint is given actually. So otherwise you need to change these values. Distance from the bottom plate. If you change the origin, so accordingly you need to calculate this also. So here we have taken origin at the bottom plate only. So this is velocity you can calculate at 0. Certainly it will be 0. At 6 it will be 0. You substitute the value of x in 0.5 mm, 1 mm, 1.5 and get the value of velocity profile using this velocity profile equation. This is the velocity profile equation. Similarly, you can calculate the flux profile equation. So say at x equals to 0, okay, at x equals to 0, tau xz is, so you can use this and get, what is this negative sign is indicating? Negative sign of the flux. Roll number 16, 16, Arka. Roll number 16, 16, Datta. Roll
Yes,
number.
sir. Hello.
So what? Why so late, man?
Sir, actually, sir, I could not unmute. Like,
So you are wasting whole class timing. Tell me,
sorry, sir. Sorry, sir.
what is this negative sign is indicating?
Sir, like, velocity is decreasing with x. Not sorry, actually, yeah, velocity is decreasing with increase in the x.
Velocity is decreasing.
Yeah.
So here it is given velocity is increasing with increasing x. This negative sign indicates
Sir, decrease in velocity, like decrease in tau.
decrease in tau, it will indicate.
Decrease in-
What is the indication of this negative sign? This is told so many times. Roll number 23, Kaushik.
Hello.
Tell me, Kaushik, what is
Yes,
the
sir.
significance of this negative signature here? Sign.
Sir, like velocity is increasing, so stress, so the stress is also increasing.
What is the physical significance of negative sign? Here
Sir, like
it's
direction.
yeah, direction. Which direction?
In minus direction, sir. Negative direction.
Minus means
Negative direction.
negative which direction?
Z direction, sir. Negative, sir.
You are not getting, man. Here all suffix are given. How you are calling it is negative z direction? So this is I am discussing z momentum flowing in x direction. So where is
Yes,
z
sir.
direction coming? So what is tau xz? Tau xz is the z momentum flowing in x direction. Where is the negative z direction is coming in here? So this negative
X.
sign indicates, what is that negative sign indicate then?
Negative sign indicates direction of momentum in x direction.
X direction.
X direction. Yes, sir.
What is this positive sign?
Sir, positive direction of stress in x direction, positive x direction.
And this negative is
Negative in x direction.
negative x direction. So
Yes,
this
sir.
shows the momentum flux in opposite of x direction. Considering origin at the bottom plate, okay, origin is at the bottom plate. So in this region, a momentum flux will be there in negative x direction, in opposite of x direction. In from the x equals to 3 mm, a momentum flux will be in positive x direction. Okay, so this will be a shear stress exerted by fluid. So you can exclude this sign. Can exclude this sign. So shear stress exerted by flowing fluid on the plate. That itself is telling me direction. Okay, so that time you can exclude this direction. So shear stress exerted by flowing fluid on the top plate and bottom plate is 6.43 Newton per meter square. And this is the maximum velocity. Maximum velocity is 9.64 into 10 raised to minus 3 meter per second. So anybody is getting these values? Anybody getting these values?
Which one, sir, for x0 and 3 mm?
Yeah, all these values.
Okay, sir, calculate.
So at least get me these two values. Remaining you can calculate at home. All the given data is in SI unit. Okay, you can note down. You should get these values. Okay, and this will be the velocity profile. If I draw this velocity value, okay, velocity at x equals to 0 mm 0, x equals to 0.5 mm 2.95, x equals to 1 5 mm 5 meter per second, and so on. So these are, it is drawn. So at x equals to 0, this is the velocity vector. This is the velocity vector. At x equals to 1 mm, this is the velocity vector. At x equals to 1.5 mm, this is the velocity vector. At x equals to 2 mm, this is the velocity vector. At x equals to 2.5 mm, this is the velocity vector, and so on. This is the velocity profile. Now, this is the pictorial representation of the model equation which we got. Okay, what is this? This is pictorial representation of this model equation, constant C1 and C2. So this, okay, this is the velocity profile equation, pictorial representation. At different value of x, I can get the value of Vz. And similarly, a flux profile. This is the pictorial representation of the model equation for flux. So this is flux profile and this is velocity profile. So now using this, you can get the actual velocity. This is the pictorial representation given a value of x. Okay, at any value of x, so at any value of x, say 3.25, so you can get the appropriate value of velocity. What is the value of velocity? Accordingly, you can get that value. Okay, and this is the value of flux. Okay, at center, flux will be equals to 0, and then accordingly, this will be in positive x direction, this will be in negative x direction here. And more importantly, when I am telling that flowing fluid on a plate, so direction is already given, so this indicates the shear stress exerted by flowing fluid on a bottom plate, and this indicates, so you need not to consider this direction when I am calling it as a shear stress exerted by flowing fluid on the plate. So this is also same thing. So accordingly, you can give the appropriate support to this plate so that this plate will be stationary. So this is velocity profile and flux profile. And this, what is the location of maximum velocity? Maximum velocity will be at the center. As soon as all three viscosities are same, the problem is symmetric. Okay, symmetric in x direction. So both resistance from both plates will be same. So it will be in between. So maximum velocity will be at the center between two plates, as this line is the equidistance from both the plates. This layer is experiencing least resistance. So least and equal resistance. Okay. So this layer is experiencing least resistance from the both plate. Moreover, momentum flux changing in its direction from the central line. Okay, so it is changing the direction. Previously it was in x direction, then it is in negative x direction. So maximum momentum flux will be at the two plates. So where you will get a maximum gradient of velocity at these two plates. Okay, so you can calculate this average velocity. So average velocity over a flow area. Flow area is 0 to b for fluid 1, b to 2b for fluid 2, and 2b to 3b for fluid 3. So accordingly, you will get a average velocity. This is average velocity. So average velocity, so velocity multiplied by area divided by area. So that will give you average velocity. This is the average velocity for fluid 1. This is average velocity for fluid 2, and this will be the average velocity for fluid 3. So you can see this average velocity is same for fluid 1 and fluid 3. And given a density, you can calculate a mass flow rate. Given a density, so average velocity multiplied by flow area. Flow area is width into b. This will be cross-sectional area for flow, and rho 1 multiplied by 1000. This will be gram per second. Gram per second. So 65 gram per second. This will be a mass flow rate of phase 1. Mass flow rate of phase 2 is 80 gram per second, and mass flow rate of phase 3 is 37 gram per second. Actually, this is mass flow rate. So this anyway, don't, this need actually, so we'll be covering this after examination, this problem. Okay. So now just I will briefly tell you what will be the syllabus for this examination. So syllabus for this examination, so this is the TP book. So you need to cover chapter number 1. So this is viscosity and viscosity estimation and Newton's law of viscosity. Chapter number 2. Are you able to see my screen?
Yes, sir.
Okay. So this chapter number 1. So this is having Newton's law of viscosity and estimation of viscosity. Chapter 2, just now we have covered shell momentum balance for velocity distribution in laminar flow. Chapter 1 and 2, then from heat transfer we have covered Fourier law of heat conduction and this thing actually estimation of thermal conductivity. So, and in chapter number 6 also we have covered actually estimation of friction factor. So this 1, 2 and some part of 6. So you consider only flow over flat plate for this interface transport fluxes. And then chapter number 9 we have covered. And then chapter number 14 we have covered. Part of this chapter number 14. This will be there in examination. Similarly, chapter number 17 and chapter number 22. This is from BSL and same is given in this book also, modeling in transport phenomena. So only the thing is, it is given in this thing actually different this thing. So we have not covered chapter number 1. So this will be a molecular transport, molecular and convective transport, chapter number 2. Then we have covered interface transport and transport coefficient. This is what we have covered. And this is evaluation of transfer coefficient. But this chapter will not be completely whatever covered in a class. So this has so many topics actually. So only flow over flat plate is covered in a class, that will be there in examination. This will be syllabus for examination. So everybody is clear with examination syllabus? The roll number 88, 75 and 94.
Yes,
CR.
sir. It's fine.
Clear, na?
Yes, sir.
Okay, so you
Yes,
convey.
it's clear.
Okay. So now we'll solve, because there are 15 more minutes. So we'll
Sir,
solve.
just one more thing.
Yeah.
Will we require anything prior to be printed on papers for solving the midterm exam?
Nothing.
Okay, sir.
So it will be a closed book examination.
Okay, sir.
So you should write your roll number and name on every pages.
Yes,
Okay.
sir.
So we can solve some of the numericals. Well, there are 15. So it is very simple actually. You take down given a data. So this is put the value and get the answer. Only if you systematically take out all the data. So this is vertical wall. So water at 20 degrees Celsius flowing down a vertical wall. Reynolds number is 10. If the kinematic viscosity of water is given, calculate the volumetric flow rate per minute, wall width, and film thickness. So this is equal to a, so you can use a model equation which we derive for flow over flat plate. Only this is the vertical wall. For vertical wall, what will be beta equals to? Beta will be equals to 0. So substituting beta equals to 0, same model equation can be used, and Reynolds number is given. So you can use the definition of Reynolds number, flow over flat plate. Something for delta, something is there, na, that flow over flat plate. That Reynolds number definition is there, and kinematic viscosity is there. So what is the volumetric flow rate equation derived, and you can correlate with the Reynolds number and kinematic viscosity and get the volumetric flow rate. And similarly, using model equation derived for this flow over flat plate beta equals to 0, so you can get the film thickness using Reynolds number and this thing. So anybody got volumetric flow rate? So you rearrange your model equation. So this is temperature is need not be used actually. It is not used at all. Reynolds number and nu. So this is the definition of Reynolds number. You can see here you will have average velocity, and this average velocity will be related to volumetric flow rate. Average velocity will be related to volumetric flow rate. So this you can see average velocity, density, and this is volumetric flow rate per unit width. Okay, width is 1. Per unit width means W equals to 1 per unit width. So this Reynolds number, this is say mass flow rate. Okay, this is mass flow rate. Rearranging this. This is volumetric flow rate. Mass flow rate divided by density per unit width. So that will be nu into Re divided by 4. Will give me volumetric flow rate per unit width. Roll number 44, Narendra.
Yes, sir.
So what is the volumetric flow rate?
Volumetric flow rate. So I'll calculate and tell you. Sir, it'll be close to 0.025, sir.
What is the unit?
Meter cube per second, sir.
Meter cube or centimeter cube?
Centimeter cube, sir.
So it is 2.5 into 10 raised to minus 2 centimeters square per second.
Excuse me, sir.
Yeah.
Sir, how this 4 is coming in denominator?
This 4 is there, no?
Actually, sir, here characteristic length should be delta, na? In Reynolds number.
Okay, yeah. No. This is defined for that modeling lower flat plate. If you remember, 4 delta is taken as a characteristic length. Look for flow over flat plate. This is another way to define a Reynolds number, where average velocity is used. One way to define a Reynolds number when we were discussing interface flux was a length from the starting point where fluid is meeting a plate. That was a characteristic length. That time we will be using bulk velocity as a characteristic velocity. Here I am using average velocity. So why here it is 4? It is no logic at all. There is no logic in that. Why there is 4? Because the person who has derived this modeling first time, he has used this 4 delta as a characteristic length and average velocity as a characteristic velocity.
Okay, so got it.
Okay, and this we have discussed this equation. Once we have discussed when we were discussing flow over flat plate. First problem we have discussed na flow over flat plate. That time I told that this is the way we have defined the Reynolds number for this case. If Reynolds number is less than 20, then flow is a laminar, not laminar. Okay, it will be a yeah, laminar or negligible rippling. Okay, so and then once you have this volumetric flow rate per unit width, so you can calculate mass flow rate again. This mass flow rate can be rearranged like this. So mu by rho is there. Okay, mu by rho per unit width. So you can calculate W by rho into W. This W by rho into W. Mu by rho is given, G is given, and cos beta is 0. So you can rearrange. First, we have calculated W divided by rho into W. So this is small w mass flow rate divided by W and take one rho. Another rho will be mu by rho equals to nu, and this is nu. So that will be nu. G is so 9.8 you can take, and cos beta is 0. Not cos beta is 0, beta is 0, cos beta is 1. So you can get the film thickness. So it is same equation we are using. This same equation which we have derived in first problem, only rearranging, and we are rearranging the equation as per given data. Roll number 57, Aman. Roll number 68, Mitu.
Yes, sir.
So what is the value of film thickness?
Yes, sir. 1 minute. Hmm. Sir, I'm getting a like a 9.2 into 10 raised to minus 3 unit centimeter.
So 9.2 into 10 raised to minus 2 centimeter. Yeah, correct. Everybody should get this. Now take down this second problem. So oil has a kinematic viscosity and density is given. If you want to have falling film thickness, same thing again, falling film. So beta equals to 0. Thickness is 2.5. Thickness is given and 1 meter wide. Width of the W is given 1 meter. What should be the mass flow rate? And check the value of Reynolds number applicable, whether you can apply the theory. So calculate the mass flow rate first of all. For calculating mass flow rate, you need an average velocity. For getting an average velocity, you need to use a model equation which we derived for average velocity, where beta equals to 0. Beta equals to 0, cos beta equals to 1. Get the average velocity. Using that average velocity, you can calculate mass flow rate, and then substitute everything in Reynolds number. Okay, for delta average velocity rho divided by mu. Calculate Reynolds number and check whether we can apply this theory or not. So this is the mass flow rate. So everything is given. Thickness is also given. Density, kinematic viscosity, thickness is also given. So everything is given, so you can get the mass flow rate. Okay. If you substitute all the values in SI unit, so you will get mass flow rate 0.2 kg per second. Okay. Now calculate Reynolds number. Are you getting these values? You can write your values in chat box. Okay. So this is the definition of Reynolds number, and this is mass flow rate. Now you can have this average velocity multiplied by density. Average velocity multiplied by delta will be equals to W divided by rho into W, and then you can substitute here. You can substitute this here and get the value of Reynolds number. Rearranging this will be a 4 mass flow rate divided by width divided by kinematic viscosity into density. That will be a Reynolds number, and Reynolds number will be equals to 5.1. And as you know, so this will be a flow without any rippling. So hence, yep, many people are getting 5.1. So similarly, you can solve the problem. Okay, this now as we have covered actually flow over flat plate, flow through pipe, flow through annulus, flow between two parallel plates. This model equation can be used to estimate this mass flow rate, volumetric flow rate, and other drag force and everything. That can be just substitute, and you go through all unsolved problem also given in chapter number 2. That will be also there. Okay, that you can go through, derive. So if say you don't have model equation, you can derive the equation. Now till now you got information and in all related things that if you have only one velocity, given is only one velocity, 1D flow, and it is varying in one dimension only. Okay, one velocity varying only in one direction, that problem can be solved very easily. That is what information you can have till now. Okay, if you have two velocity, how to take that will cover after examination. But at least given one velocity, one dimensional one direction velocity is there, and it is varying only in one dimension. It is varying in one direction only. That problem can be solved very easily. Whatever it problem can be, geometry can be different. Okay, so we have covered Cartesian coordinate, we can cover cylindrical coordinate. So you can see some of the problems are there in unsolved problem, spherical coordinate system also. Okay, and some of the problems are there variation in 2 dimension, but that can be converted into 1 dimension. Substituting 1 dimensions variation and all. So you go through all these unsolved problem that will be there in examination. Okay, so this is just we can use this Hagen-Posk's equation. Everything is given. So this will be 7.5 into 10 raised to minus. This is volumetric flow rate through annulus. Okay, this is the definition of Reynolds number. Okay, this is the definition of Reynolds number for flow through annulus. So this is the mass flow rate. Okay, mass flow rate for this thing. So you can substitute and get the answer. So this will be there for examination. Everything what we have covered till now. Only what we have not covered in estimation of heat transfer coefficient, mass transfer coefficient, momentum transfer coefficient from chapter number 4, which is not covered in a class, will not be there in examination. Otherwise, chapter number 2, 3, 4 from Ismail Tashan book, chapter number 1, 2, 7, then 9, 10, not 9, and 13, I think, 13, and then some 16 and 21. That interface flux and thermal conductivity, these will be there in examination as discussed. Anybody has any questions over here? Okay, then, thank you very much. So all the best for examination.
Excuse me, sir.
Yeah, tell me.
Sir, I had the query in the question which is based on the capillary tube.
Oh, just hold on, I will share. So, sketch.
So, can we approximate capillary tube as a pipe and then apply Chilton-Colburn analogy in this question? Hello?
Yeah, but why you need to use Chilton-Colburn analogy here?
So from here, I'll get the friction factor, and then I know that the power that the pump should apply, that should be able to overcome the work done by the drag force.
Okay. So that all data is given, no, viscosity is given.
Yes, sir.
Kinematic viscosity is given, density is given. If Reynolds number is less than 2100, why you are going for friction factor then?
Sir, once I get the friction factor, I can calculate the drag force.
But using these also you can calculate drag force, na? You can calculate shear stress on the wall, na?
Yes, sir.
You have flux profile. Using that flux profile, you can calculate the drag force exerted by flowing fluid on a wall.
Okay, sir.
Can't you get this drag force using this model equation? Velocity profile here, velocity profile you have, stress profile you have. Calculate the stress stress exerted by flowing fluid on a wall multiplied by area, that will give you drag force, and that can be, using that you can calculate the pump capacity.
Yes, sir.
So look, where here also you can use a friction factor. Here also you can use a friction factor, provided you will have engineering correlation for that.
Yes, sir. So I use Chilton-Colburn for that, sir, because I know the Stanton number for mass transfer, and I can also calculate.
Where is Stanton number is given?
Okay, sorry, sir. Sorry. Okay. Sorry, sir. Got confused between the question. Yes, sir. Sorry.
Yeah, this is purely momentum transfer problem.
Yes, sir. Sorry. Yes.
Purely momentum transfer problem.
Yes, sir. Sorry, sir. I got confused between the question.
Okay. Okay, then all the best for examination.